Alright, silly people, here's the situation. We have a sphere that is split in the middle, um, where the top half is kept at a time-dependent electric potential of V cosine omega t, and then the bottom half is kept at minus that value. Um, it's at radius A, and we need to find the um, radiation fields in the limit where the wavelengths are much longer or much larger than the wave size of the system. Okay, so the equation that Jackson gives in his book um, for the vector potential, the equation that I'm talking about is this guy, is mu naught I k r over r uh, lambda, or sum over n minus I k n over n factorial um, integral of j as a function of the position of the source, and then it's n dot uh, x prime n d3x prime. That is the Taylor series expansion of the vector potential in the limit where the wavelength is much larger than the size of the system. Okay, now that we have this nice expansion form, we're actually just going to not worry about any values where n is greater than 0, because again, the size of the system can be treated as small, so we're just going to let n equal 0 anywhere that it shows up. So that means that we're actually looking at mu naught over 4 pi e to the I k r over r times the integral of j of x prime with respect to d3x prime. I mean, that's all we're doing. So you can do a little bit of an integration by parts on this thing. You can say that your u is equal to your current density. Your du is the divergence of said current density. Your dv is just your volume element, which has a result of 1. So writing in your substitution there, you have that ax is equal to, with the constants out front, I'm just going to combine them into one term, u naught e to the ikr over 4 pi r. And then uv, so it's just j of x prime evaluated at infinity, plus the integral, or minus the integral of the divergence of the current density with respect to dx prime. So the current density evaluated at infinity is obviously 0. And you can use the continuity equation, that is that the divergence of the current density plus the partial derivative of the charge density with respect to time is 0, to rewrite this now as you have mu naught e to the I k r over 4 pi r. I'm running out of room, but it's just going to end up being the integral of the time derivative of the charge density. Right. You can assume that the charge density is harmonic. That is, it's going to be proportional to some constants times e to the minus I omega t. That is that the time derivative is just going to be minus I omega times itself, right? So nothing too crazy there. And then plug this into your integral. So you have that the vector potential is mu naught e, that's an ikr. You have 4 pi r down here. You're doing the integral of I omega rho over d3x prime. And that is pretty much just the definition of a dipole. Right, so you can pretty much just treat this as a dipole now, since you have two spheres with opposite potentials. I'm going to be treating it as a dipole P, without knowing what that dipole moment actually is. But we're going to be able to find it when we compare this vector potential to the scalar potentials for two conducting shells, which is a different problem in Jackson. It's back in chapter 3 where that the electric potential, scalar potential, for one of these funky little sphere combinations is just the V, and then we have the 3/2 a over r squared p1 cosine theta minus 7/8 a over r to the 4th p3 cosine theta plus 11/16 and blah blah blah. I don't matter. Yeah, I really only care about the first term anyway. That is the expansion of the potential in Legendre polynomials. But also see the multipole expansion of scalar electric potential, where instead of being a function of r and theta, it's a function of x, which is going to be given by 1 over 4 pi epsilon naught q over r is the monopole term, and then the dipole term, and then the multiple terms, which I don't really care about right now. The cool thing is that this term right here matches the dimensionality of this term. So what do I mean by that? Seeing that our spheres are stacked on top of each other like this, that is, the multipole will actually point in the z direction. So you can evaluate your electric potential along the z direction, and at just some arbitrary point z in the z hat direction, and then p is also in the z hat direction. That means that p dot x will just be zp. Yeah, it's just zp, and you can take z, translate it over to spherical coordinates, and call it r cosine theta. So you have pr cosine theta. So matching the first term in the Legendre polynomial expansion to the second term in the multipole expansion, you have 3/2 a over r squared p1 cosine theta plus, or is equal to, 1 over 4 pi epsilon naught. And then this is r p cosine theta over r squared. Now it's easier to see why these two terms have matched dimensionality, which is why we can compare them like that. And we can use this to solve for p once we note the fact that the first order Legendre polynomial of cosine theta is just cosine theta. So that cosine theta will cancel out this one. You can solve for p by saying it'll be 3a squared over 2 times 4 pi epsilon naught, and then this should be cubed, but that's okay, will equal p pretty much. So it's 6 pi a squared epsilon naught. will be the magnitude of your um, stupid dipole. And I forgot that there's a V on here, so that's a V there. So that's a V here. So that's a V here. But we know that the magnitude of V here is not a constant. That's the time varying potential. It's the time varying potential on the surfaces of the spheres, which have magnitude V cosine omega t. So we have that the time varying strength of the dipole is actually 6 pi a squared epsilon naught V cosine omega t. And then that's going to give you what you want. So now we can throw this into our vector potential. So that's now going to look like we had a minus z hat on this guy. So if we turn this into a vector, it's going to be pointing in the z hat direction. We have mu naught e to the I k r. We have 4 pi r, and we have our new term 6v a squared pi epsilon naught cosine omega t, which we can simplify some more. So it's going to be the pi's are going to cancel out. The mu naught times epsilon naught turns into 1 over c squared, and then you get just 3 e to the I k r. It's a minus sign on all of it. 2c squared r v a squared I omega cosine omega t in the z hat direction. Yeah? Okay. So that's the vector potential. We can actually find the radiation fields now. So that's going to be that the H is equal to 1 over mu naught, and it's going to be the curl of the vector potential, and then the electric field will be just I over k times the ratio, or the square root of the ratio of the permittivity to the permeability, times the curl of H. So we're going to have to calculate H first anyway, so let's just do it. It'll be the curl in spherical coordinates is 1 over r sine theta, and then all we have is a z component. So we're going to end up having something which points in the phi hat direction, and we're taking a derivative with respect to theta. So it's sine theta 3e to the ikr over 2c squared r. We have va squared I omega cosine theta, pointing in the phi hat direction. So that derivative can be a little silly, and we're going to end up neglecting a part of it, and you'll see why. So moving the prefactors out, you'll have minus 3e I k r, you'll have va squared, you'll have I omega, you'll have 2c squared mu naught r squared sine theta, right? And then we're going to turn the identity of sine theta cosine theta into 1/2 of sine 2 theta. So we're actually going to make this into a 4 out here, and we're doing the derivative of sine 2 theta. Which turns into 2 times cosine 2 theta. So we get that the denominator is back to having a factor of 2. We got 2c squared mu naught r squared sine theta cosine 2 theta. And let me just make sure. Yeah, I think we can actually simplify, since epsilon naught mu naught is equal to 1 over c squared. If we multiply 1 over c squared by mu naught, then you'll actually just have um, epsilon naught up top. Yes, okay. So just reducing the amount of universal constants in our answer, we have just epsilon naught up top, and then 2r squared sine theta on bottom with a cosine 2 theta there. That's in the phi hat direction. I don't think it gets much simpler than that. So we can go ahead and move on to the electric field, um, which is going to be, in this case, again, it's I over k root mu naught over epsilon naught times the curl of h. So that was h that we did there, not e. E is I over k times square root of mu naught over epsilon naught. We have all of our constants, which is going to be 3va squared I omega epsilon naught cosine 2 theta over 2 sine theta. I'm pulling out all the theta terms because our magnetic field was pointing in the phi hat direction, so the only thing that we are taking the derivative of is with respect to r of the r-dependent stuff, and then the result is going to be pointing in the theta hat direction. So that integral, that derivative isn't too bad. I'm going to try and simplify the stuff that we have in here. We have square root of mu epsilon naught over epsilon naught times epsilon naught. So you're going to end up with the square root of mu epsilon, which is c squared, or 1 over c. It's 1 over c. Okay. 3va squared. We have a minus sign now because you have two i's. It's omega cosine 2 theta over 2kc sine theta. Cool. And then the derivative, pointing in the theta hat direction, is going to be, we're going to have to do a little bit of quotient rule. So r squared times ik e to the ikr minus e ikr, and then multiplied by 2r, so minus 2r, and then all over r to the fourth. Okay. That can be simplified. We can pull the exponential term out. So minus 3va squared omega cosine 2 theta. And then we have e to the ikr. We have divided by 2kc sine theta. We'll have a r squared on the bottom. Yeah, r squared on the bottom. And then in here, you'll just have ikr minus 2. So we can only, we'll have a r cubed on the bottom, actually. R cubed sine theta. Okay, so the whole point of this problem is that we are in the limit where the wavelength is much larger than the source of the system again. And so I don't think it's too egregious to make the approximation that IKR is going to be greater than 2 by a lot. So that will actually help us out in getting our dimensionality correct. So now we're doing minus 3 VA squared omega cosine 2 theta e to the IKR. And then we'll have IKR, not even IKR, just IK. And then now we'll have our desired R squared on the bottom. So the electric field decays as it should. Okay, we need to find the angular distribution of the radiated power, i.e. the change in power of the field waves with respect to omega, which in Jackson is given by r squared over 2 times the magnitude of the pointing vector. And we'll actually have to take the complex conjugate of our magnetic field for this to work. So remember, we had a minus sign on the I in H, and then we had a minus sign on the I in E, as we just saw. So you end up with an overall minus sign when we look at the cross product of the two. So it's going to be minus, we're going to have an r squared over 2 out front, minus 3v e to the I k r a squared omega cosine 2 theta I k over 2kc r squared sine theta. That's the electric field prefactor stuff. And the magnetic field prefactor stuff was 3 epsilon naught. We had e to the minus ikr now because taking the complex conjugate, we got to flip the sign on the exponential, which does mean that our exponential decay stuff is going to end up being tossed out the window. You'll end up with 2r squared sine theta cosine 2 theta over there. And then the things that you're actually taking the cross product of is just theta hat cross phi hat, which has the result of minus r hat, so everything is good there. Then the magnitude is r squared over 2 times the positive version of this stuff. So 3 squared is 9, we'll have v squared, the e's will cancel out, you'll have a to the 4th, you'll have omega squared. I end up with 2 factors of I, which will give you -1, but they didn't take the magnitude, so it's just 1, pretty much. And then on the bottom, you'll have 4kc r 4th sine squared theta, and then you'll end up with 2 factors of cosine 2 theta. And there's an epsilon not here, which is funny. We can simplify that. So it's going to be r squared over 2. Actually, let's go ahead and factor that r squared through. So 9v squared a 4th omega squared. Epsilon over the square root. No. It's epsilon times the square root of mu epsilon. So it's just square root of mu times epsilon. Man, I don't think it's much nicer at all. I'm going to leave it how it is. Epsilon over 4kc r squared sine, and actually 8 down on the bottom, sine squared 2 theta, and cosine squared 2 theta. I don't think it gets much nicer than that, actually. Cool. Then we can find the total radiated power by integrating over solid angle. So that was dp d omega. P then will just be the integral of that stuff over phi and theta. So, I mean, there's no phi dependence in here, so you'll end up with an overall factor of 2 pi, I think. And then we have to integrate the theta dependent stuff. So let me write all the prefactors out. 9v squared a fourth omega squared epsilon naught over 8kcr squared. And then it's the integral of cosine squared 2 theta over sine squared theta d theta. Or actually sine theta d theta, because that's the proper integrand. Yeah, that's the proper Jacobian. And we're integrating from 0 to pi. And so without showing the integral, just saying that it evaluates to pi halves because I'm evil, you'll find that it is 9 pi v squared a fourth omega squared epsilon naught over, actually have pi squared here, and then 8kcr squared. That's going to be your total radiated power. I think I have an extra factor of k where I shouldn't. Yeah, okay, there it is. So, literally just left the factor of k sticking around where I shouldn't have, so it will cancel out on this line here. There. Which means it will cancel out here. So we shouldn't have a k on the denominators here. Okay. Then everything's cool. Nice.